This is Dr. William McLeod. Today we're going to talk about waves. We're going to talk about travelling waves and stationary waves. So one question we could ask is, how would we describe what a wave is? Well, a wave is a disturbance transferring energy as it moves, and there's no net mass transfer. Now, the simplest sort of mathematical way of describing a wave is as a cosine or a sine wave. So that's really a sort of brief description of what a wave is. Why bother studying waves? Well, waves have a huge amount of applications. We could think about electricity generated by water waves. We could think of electromagnetic radiation used in mobile phones, radar, fiber optics, and the list goes on and on. And the study of waves helps us understand huge big events such as earthquakes, and also very small things such as the study of quantum particles such as electrons. So it's a very important area of study. Now let's think about how we can sort of describe waves. We can talk about waves in terms of phase difference. So if we've got two waves which are out of sync by a distance of x, the phase difference can be described as x divided by lambda, the wavelength, times 2 pi. So the phase difference is given in radians because 2 pi radians is one oscillation of a wave. We've mentioned that waves transfer energy, and the general sort of relationship is energy is equal to k, a constant, times the amplitude squared. And then down at the bottom of the slide there, we can see we've got a number of equations which are used extensively in advanced higher and D-level physics. So let's just look at the two equations at the bottom there, where y is equal to a, the amplitude, sine 2 pi, and then in the brackets here we'll get ft, frequency times time, minus x divided by lambda. So x is the distance that the wave has travelled to the right. If we're talking about the distance travelled to the left, we say we use the relationship plus x lambda. And then I suppose the equations y is equal to a sine omega t is quite important as well, because that is sort of general description of waves, isn't it? And omega is the angular velocity, which can be described as 2 pi times the frequency. So let's now think about stationary waves. Stationary waves are also known as standing waves. So standing waves or stationary waves, they don't propagate through space, but they're confined in space. They're confined in a specific region. Now, applications of standing waves are, for example, musical instruments. So plucking a guitar string, that would be an example of a standing wave, or a woodwind instrument where the wave is confined in a space, a specific space. And then other applications are quantum particles, such as electrons, which are confined in a space as well. They can be described in terms of standing waves. And I talked a little bit about that in a video I made a while back on quantum mechanics. So how would a standing wave look? Well, it's not propagating through space, but you would see it sort of vibrating up and down. And I've got sort of like diagrams, images of the standing waves on the left-hand side there. The top one is the first harmonic. So this is the lowest frequency, and that would look like a half a wave vibrating up and down. And then we've got the second harmonic and the third harmonic shown. A couple of definitions. The node is when the amplitude is 0, and the antinode is when the amplitude is at a maximum. So only, as we can no doubt see from those diagrams, only certain wavelengths are actually allowed in standing waves. Only certain frequencies, only certain wavelengths are allowed. And this, the wavelength can be described mathematically as lambda n, so n being the harmonic of interest, is equal to lambda 1, the fundamental wavelength for the first harmonic, divided by n, the harmonic of interest. Now let's think about interference patterns. So in higher physics, we learned a little bit about that, did we not? And how you can only get an interference pattern by using coherent waves. A coherent wave is described as a waves which have a constant phase difference. So to get constructive interference, the waves would need to be out of phase by an integral number of 2 pi radians. In other words, full wavelengths would need to be out of phase, so that a peak would meet a peak and a trough would meet a trough. Destructive interference is when the waves are out of phase by half a wavelength or pi radians. So how do we get a constant phase difference so that we can then see an observable interference pattern? Well, one way is by taking advantage of what's called the optical path difference. So let's say we've got a wave going through just air, and then we've got a wave going through air and glass. Now the wave, light traveling through glass will be going slower. So when it emerges from the glass, it'll have a wave difference, it'll have a phase difference from the wave which has not traveled through glass. So that's one way of getting a constant phase difference, which then can be used to make an interference, to get an observable interference pattern. So another couple of ideas which are interesting in getting constant phase differences, so you can get interference patterns, is the idea that when a wave reflects off a higher density material, such as light waves hitting off glass, the result is a crest reflects as a trough, and a trough reflects as a crest. So you get a phase difference when a wave reflects off a higher density material. Now at the bottom of the slide, on the bottom left-hand side, we've got a wave which has been reflected and refracted, and this creates a phase difference which can then be used to get an observable interference pattern. Now, one example of quite a nice interference pattern is when you get oil on top of water and you see a multicoloured pattern. I'm sure we've all observed that maybe in a road, just after it's rained, there's maybe a little bit of oil and some water, and then you get this nice multicoloured pattern. So the oil appears multicoloured due to waves being reflected from the top of the film or reflected from the water-oil interface. The result is an optical path difference. Some colours will be reinforced, constructive interference. Other colours will be destroyed because of destructive interference. So this optical path difference results in the nice pattern that we see in oil-water mixtures. Now, another application, a very interesting application, I think, is the thin wedge interference by division of amplitude, which can be used for measuring the thickness of a very small object. So let's say you've got something even as thin as the hair in your head, and you put it within 2 glass plates. Well, that will create a slight wedge. Now, that slight wedge then will create phase differences from the light which goes into the glass and reflects off the glass. So that's sort of demonstrated on the diagram there on the left-hand side there. So this then is able to create an observable interference pattern. So mathematically, we can describe that delta x, the distance between the minima and the maxima, is equal to the wavelength times L, the length of the glass plate, divided by 2d, the width of the open end of the wedge. So that width would be the thickness of the small object you put within between the glass plates. It's a very interesting application. Now, an experiment we're all familiar with from higher physics is this Young's slit double slit experiment, where you get interference by division of wavefronts. So you get maxima at very specific positions on the screen. So that can be described mathematically as d, the distance between the slits, sine theta, you can see where the theta is in the diagram there, the angle, is equal to m, so that's the maxima. So you get the zero order maxima, which is m is 0, that's one right in the middle, and then you get maxima at specific positions, 1, 2, 3, above and below it, so that's m, these different maxima times the wavelength. When the theta is very small, you can use the equation delta x, which is the distance between the maxima, is equal to lambda, the wavelength, times d, the distance between the slits in the screen, divided by d, the distance between the slits. So that's when you can use that equation for the when the theta, the angle, is very small. Now let's think for a moment on polarized and unpolarized light. So unpolarized light, so that is when the light is vibrating in all different directions. You can polarize it by putting it through a polarizing filter. So you just get the light vibrating in one direction. That's one way of getting linearly polarized light. Another way of getting polarized light is by reflecting the light off a block of glass. So some of the light will be reflected off the block of glass and some will be refracted. So when the angle of refraction and the angle of reflection is 90 degrees, that is known as the Brewster's angle. And at this Brewster's angle, the reflected ray is polarized. So that's another way of getting polarized light, by taking advantage of the Brewster's angle. And that can be described as n, the refractive index of the glass, is equal to tan I being the angle of incidence. Okay, so let's think of these images we've got here. We've got a couple of photographs there, a few photographs showing polarized and non-polarized light. So what can be abundantly clear by looking at that is that polarized, the photographs taken by a camera with a polarized lens shows very clear images. We get nice clear images of water. We can see the rocks clearly. We can even see the fish in the water with using polarized lenses. Another use of polarized lenses, as well as taking maybe nice photographs, is in 3D cinema glasses. So each eye sees a slightly different image. So the left eye will see a different image from the right eye because the light has been polarized in a different direction using different filters in the glasses. So this results in an image which appears to be three-dimensional. So let's summarize what we learned from today's presentation. So we talked about phase difference. We looked at the equation for phase difference. The phase difference being measured in radians. We looked at standing and stationary waves and how to work out well, the equation for related to that, the wavelength of the different harmonics. We thought about interference patterns and how coherent waves to provide these interference patterns can be got by using division of wavefronts. We thought of the Young split experiment. You can also get division of amplitude, where a wave acquires phase difference because of reflection and refraction. We looked at the interference pattern on an oil-water interface and the nice colours you get in that because of constructive and destructive interference. We looked at thin wedge interference, where we can measure the width of a very small object between two glass plates because of this interference pattern. We thought about polarized light and how to get it via the Brewster's angle and also by using polarizing filters. And then we looked at these equations I've got there, which are used quite extensively in advanced higher physics and A-level physics. So let's now think about some past paper questions. These ones are for advanced higher physics, SQA, but relevant to other exam bodies as well. So a ship emits a blast of sound from its foghorn. The sound waves as described by the equation. So we've got the equation there, where the symbols have their usual meaning. Determine the speed of the sound waves. So I've got the general wave equation put down there. So from that general wave equation and comparing it to the equation above, we can work out that the wavelength is 1 over 0.357. So, and we can also work out from that equation that the frequency is 118. So combining those things and putting it into speed equals f lambda, we work out that the speed is 331 meters per second. Okay, the sound from the ship's foghorn reflects from a cliff. When it reaches the ship, this reflected sound has half the energy of the original sound. Write the equation describing the reflected sound wave at this point. So we know that the energy is equal to k times amplitude squared. So energy over amplitude squared is equal to energy over amplitude squared at other distances. If we know that the energy is has halved, and we know that the amplitude is 0.25, then we can work out the new amplitude, which is 0.177 meters. So we can put that into our equation. Remember our equation here, and then we've got we can see the equation at the top of the page there. We put that into our equation, and instead of minus 0.357x, we put plus, because the wave is now going in the back, is going left now. So it's changed direction. So there we have it. That's the equation. Now we're thinking about a stationary wave. So we've got a signal generator, and we've got a specific size of container there with a closed end. The question is, explain how the stationary wave is formed. And the stationary wave is formed because the incident ray interferes with the reflected ray, and that's how you get these stationary or standing waves. Now, at one frequency, in the next question, at one frequency, the microphone detects a loud sound. The frequency produced by the sound generator is now increased gradually. Describe what happens to the loudness of the sound detected by the microphone as the frequency has been increased to twice its original value. Well, sound will become quieter. Then when it reaches a loud frequency, like the loud frequency, you start hearing it again. So as we know, certain wavelengths, certain frequencies are allowed within standing waves. Not all frequencies, not all wavelengths are allowed. So until you reach a loud frequency, you won't hear the sound. But when the loud frequency is reached, you can then hear the sound again. So the sound becomes quieter, and then it becomes louder again. Okay, so on to the next question there. An electromagnetic wave is traveling along an optical fiber. Inside the fiber, the electric field vectors oscillate as shown in the diagram, or the figure A. So we've got a nice equation there for the wave. So the question is, 2 points A and B along the wave are separated by a distance of 4.25 times 10 to the minus 7. Calculate the phase difference. This is the phase difference along the wave itself, so between points A and B. So we've got the distance x, and the wavelength can be ascertained by looking at your wave equation at the top there. So we plug it into our phase difference equation, and we end up with a phase difference of 1.72 radians. Next question. Another 2 points in the wave, P and Q, have a phase difference of pi radians. State how the direction of the electric field vector at point P compares to the direction of the electric field vector at point Q. Well, 2 pi radians is a full wavelength. Here we want about half a wavelength, which would then necessarily mean you're getting a difference in direction, aren't you? Because it's half a wavelength. So show that the speed of the electromagnetic wave in this optical fibre is 2.03 times 10 to the 8 meters per second. Well, for that, we need the frequency and we need the wavelength. So we look at our equation and we can work out the frequency from that equation. We can also work out the wavelength of that equation by comparing it to a standard wave equation. We plug in these numbers and we get we do indeed get 2.03 times 10 to the 8 meters per second. Okay. A wave travelling along a string is represented by the relationship. So you've got the equation there. Show that the frequency of the wave is 147 hertz. So again, you compare that to your standard wave equation and you can work out from that what the frequency is. So I've sort of written it down there, and it does indeed appear to be 147 hertz. Determine the speed of the wave. Again, you get the frequency from the wave equation above, and you use that, well, the wave equation above, and you multiply that by your wavelength. Again, you get that by comparing the wave equation you've got above there with the standard wave equation, doing a little bit of algebra on it to get the lambda, the wavelength. So you put the frequency and the wavelength together and you end up getting the speed to be 205 meters per second. Now, the next question, the wave loses energy as it travels along the string. At one point, the energy of the wave has decreased to 1/8 of its original value. Calculate the amplitude. Well, if the energy has decreased to 1/8 of its original value, you use the relationship E equals amplitude squared is equal to E over amplitude squared. And if you know it's went to 1/8 of it, you can actually then work out from the original amplitude what the amplitude is now, which is 3.36 times 10 to the minus 4. This question here is about, the last question we'll do, is about standing waves. So explain briefly in terms of superposition of waves, how the stationary wave is produced. Well, waves is reflected from each end of the, I suppose, the guitar, and they interfere, creating maxima and minima. So you get the incoming wave interfering with the reflected wave. And in part 2 there, we've got a diagram of the fundamental, the first harmonic and the third harmonic, fundamental frequency and the third harmonic. So determine the frequency of the third harmonic. Well, we need to understand what's happening with the wavelength there. So the wavelength, so the speed is the same, but the wavelength is now divided by a third because it's the third harmonic, and therefore speed equals f lambda. It means that the frequency, if the speed stays the same, it means the frequency has tripled. Okay, so that's us finished with the presentation today. I hope it was of some use to you. Okay, bye then.